I've been asked to speak about data-driven initial conditions for heavy ion collisions, and this is something that Wilke and I have been working on for years, actually. And there's already one paper out since June, and this one hopefully soon, but I've already changed this what used to be a 2208 or something into a later date multiple times, so who knows.
First the high. Put up. Yes, yeah, high.
Oh yeah. So we did both of these works with Projectum, which was developed at first at Utrecht, and then I moved to MIT, and Wilke moved to CERN. And in September, I'll be moving to CERN, so we can keep the slide the same. And it contains basically all of the components that you need, except for the afterburner, inside a single executable. So the initial stage, the hydrodynamics, and the freeze out are all done automatically. And that also contains an analysis suite that automatically analyzes your all of your results in the same way that the experiments do, and produces easily openable things that you can plot in Mathematica. Everyone I've spoken to finds it very easy to use because everything is so automated. You don't have to worry about formats or unit conversions or whatever. We also distribute the parameter files that we use to generate each paper alongside the source code. So there's a folder where you have a bunch of archive numbers, and you can just go to each archive number and run it for yourself to if you're interested. It's also quite fast, and it's fully parallelized. So this figure takes around 21 hours to compute on a laptop. So it's pretty fast. And just to see why that's relevant, like for the Bayesian analysis, you need around 1,000 of similar computations to this one. So the faster, the more you can do. And also the fact that it's fully parallelized means you can easily put it on a cluster, run it on 1,000 different nodes, collect the results, and then it generates a single plot for you if you want. And it's publicly available at this this website. So if you want to give it a try, you can download it there. So I've listed the components that go into Projectum here again, just to be able to say what I'll be covering in this talk. So in the introduction, I'll briefly, it doesn't work that well. I'll briefly cover the hydrodynamics and particleization just to make sure everyone's on the same page on like what we're doing there. But I'll spend most of the time in the initial conditions, which I was asked to cover, and what is also the main focus of these two papers. So starting with hydro, really the hydro is in essence it's sometimes called the ultimate effective field theory. It's basically you look just at conservation laws. So for example, what you solve in absence of any flavor currents is simply the conservation of the stress energy tensor. But then you don't have enough equations to be able to solve this, because this T mu has 10 components and there's only 4 equations there. So you need some ansatz, which is assuming that everything is very close to equilibrium, and then you do a derivative expansion. And then you can say, for example, at first order in the derivative expansion, you get these two terms for the shear and these two terms for the bulk. And then at second order, you get this whole 14 moment approximation. And here I'll also briefly mention the color coding. So since this presentation is going to be the result of a Bayesian analysis, throughout the entire talk, I have at least tried, I might have missed a few, but like I've tried to color green all parameters that we vary in the Bayesian analysis. and in red, any parameters that could in principle be varied, but we kept fixed for computational well, reasons, like you cannot do everything. So we kept some of them fixed. And the only thing you need to really remember from this slide for the rest of the talk is this 14 moment approximation. I'll bring it back when it's needed. Yes?
But why do these three?
Oh yeah, people always ask. So of course we kept eta and zeta because they're the first order coefficients. Then we kept this relaxation coefficient, or this relaxation time, it really is, because we wanted to look at second order coefficients at some point 3 years ago.
Actually, what is 14 moments approximation?
Where does the name come from?
No, what's the idea behind this?
Oh yeah. Well, the idea is basically that you write down all possible. You do this derivative expansion. You write down all possible expressions with two derivatives, and then you look at the second law of thermodynamics to get rid of some of the coefficients that violate the second law, or you, like for example, where these signs come from is that you find that you can only satisfy the second law if eta is positive. So then it makes sense to put a -9 here. Otherwise, it would always have to be negative.
Then you'll get 14 moments. So.
I think if you include flavors, maybe I don't know how this historically went.
Current. So there's red, the moments of the Boltzmann equation.
G mu nu is 10 and J mu.
Yeah, 4 of those were the currents. We should not actually use it here.
Yeah, okay. So maybe I should call it the 10.
Okay, so G mu nu is 10 because it's a traceless.
No,
It's symmetric. Symmetric. Also, all terms are.
Yeah, symmetric.
Okay.
It's a 4 by 4 symmetric by symmetric.
And it's, yes, and the 14 moments reduces to 10 if you don't.
Yeah. Yeah, I mean, we always still call it the 14 moment approximation. But,
Oh, I see. So that's why you're sharing Bob. Okay, then the current.
Yeah,
the current
so-
means which current?
yeah, there's no current here.
No,
So
no,
that's,
if you have a,
for example, baryon number or
that
charge.
give you four degree or 4 moments. I see. So this is already like 10 equations effectively.
It should be, yes. Well, I mean, here you have 4 equations, and then this is symmetric traceless. So this is really 5, and then this is another 1. So yes.
You tell us how you fix the red parameter.
Yeah, so, well, I should first maybe try to finish the answer why we chose the green ones. So the first order ones are, well, make sense why we did those. Then at first we tried varying this one, and this one, and then we later got rid of this one. You basically expect the relaxation times to be the most important. So that's why at first we chose this one and this one, but then it turned out the problem with this one, the bulk relaxation time, is that we just didn't have any sensitivity to it because our bulk viscosity was so small, because this guy is proportional to the bulk viscosity. So, so since we didn't have any sensitivity to it, we stopped varying it. As to why we only chose this one out of all these other second order terms, it's basically just a random, more or less random choice, because you cannot vary all of them. Well, you can, but then you increase the computational cost. So we decided to just pick one and see if you can get constraints for one of them. And then, I mean, if you cannot do it for one at the same time, then you can probably not do it for all of them simultaneously anyway. So we fixed the red values to the kinetic theory results.
What kind of kinetic theory?
Sorry, but since this is a bit scary, I think for people who are not in the field, I think we should also maybe point out that all of these coefficients, the red and the green, they are probably of very little importance for what we are going to discuss in this workshop. It is the connection to
That is
nuclear structure.
Yeah, that's why there's only one slide. If I knew there would be questions, I would have made more slides.
I think it's very interesting, but it's not it's out of the point.
Yeah, that is.
I think we could do I think a very good job, isn't just ideal hydrodynamics. Probably, so it would be interesting actually to figure out what you can add, which predictive power you can add by putting in viscosity, but it's not very clear to me actually.
So maybe we just move on to the.
Oh, that's an important question though, like how, to what extent the final state parameters could influence, right? Can we set some kind
You
of,
said before the isobar ratios,
Yeah,
I think
sure.
just everything just goes away.
yeah. Small residual, you do see a small difference, but.
Okay,
I
so
mean, the viscosities do erase over time the granularity of the initial state.
Yeah.
Right. And so in that sense, they do matter. If you are only interested in the deformation, maybe their importance is not so big, but if you're really interested in the initial state,
Okay.
at a more precise level, they do matter.
Yeah, so I think this is the kind of things we should discuss.
So if you erase it, as long as you don't fully erase, then if you take a ratio, you still see.
They erase the spatial non-homogeneities and map them onto momentous ways, so they do matter.
Right, but in the early time, as you will still get some response in the early time. Then of course part of that is erased, but you should still see diluted signal, and that diluted signal we still have the same trend as functional centrality.
And we are making precision hydrodynamics nowadays, so I think these back of the envelope arguments don't cut it.
Oh, but in the MPT model, we does vary the shear viscosity by factor 5. And the V2 value are dilute, the V2 value change a lot, but the ratio are very stable.
What ratio?
Well, the V2 ratio, V3 ratio, because the
Ratio between what and what?
it in the isobar.
Okay.
The reason is that the V2, when you erase the signal, you not only erase, you're going to erase the impact of nuclear structure and the typical and other contribution by the same amount. In that sense, you will, if that's true, then you still see the same signal. But if you erase the contribution from nuclear deformation and the original, the contribution from the original, fluctuation or centrality dependent eccentricity by different amount, then I agree with you, you will see a change. But somehow we see they're reduced by almost the same amount. In that model.
If you stick too close, so as close to each other in mass number as you do in that case.
Yeah.
There are small effects from the deformation.
but maybe we should move on. So our particleization is also pretty standard. We have a freeze-out temperature, which we vary in the Bayesian analysis. And at that temperature, we turn the fluid back into particles. And that we do by sampling thermally and then boosting with fluid velocity. And then we use the BTB prescription to match the shear coefficients, the shear tensor and the bulk pressure, so that the stress tensor is entirely smooth, or at least continuous. It's a Pratt-Torrieri-Bernard.
Why do you need a prescription for doing that matching?
It's the one historically we implemented first. And,
why do you need any prescription? I mean, you calculate T mu from the.
Well, but how to do the viscous corrections in the, like Jetscape had a paper on this, that there's a couple of different prescriptions and
This is
no,
calculating the
Sorry,
particle
this is the hadronization.
Yes.
Okay, I was
Which I gave you.
at times, sorry.
I'll get to the earlier times.
Okay.
And then, so after particleization, we feed the particles into SMASH as our hadronic afterburner to, well, get some more final state interactions. So that's basically the simulation part of it. And then we use the code to do a Bayesian analysis. And Jean-François already already discussed this in his talk extensively, so I'll also go through this quite quickly. So the main problem is that we want to fit 25 parameters and we have 653 data points. And if you try to do that, then there's two problems. I mean, I just told you that Trajectum is very fast, but then here I'm going to tell you that it's too slow. So it's too slow to use it directly. And another problem is the parameter space is very large. If you, for example, decided to per parameter have 10 points in a grid, then you have to evaluate 10 to the 25 model evaluations. Well, good luck with that. That's not going to work. So the first problem that the model is too slow, you basically solve by introducing this Gaussian process emulator, which emulates your model. So you basically replace your model, which evaluates say 20,000 events in a day, by something that evaluates it within a millisecond, which is of course a lot faster. And then Jean-François didn't really say this in his talk, I think, but like for me, at least, the main reason why you would do Bayesian inference instead of like just looking at chi-squareds is this problem that the parameter space is very big. So you just cannot scan the entire parameter space and just compute chi-squared everywhere. And in a Bayesian setting, you can treat the problem as with a Markov chain Monte Carlo.
Because we didn't use an emulator.
Yes.
So will you do that by, I mean, if you go back to all these parameters, it's still too, I mean, like you say, oh, we cannot do it because it's just too costly. But even you use an emulator, even with the emulator, it is costly to vary all your parameters.
Well, I mean, say you have 25 parameters. Say you want to evaluate chi-squared in a grid, and you take a very coarse grid, say 10 points in every dimension. That's 10 to the 25 evaluations. Even if your model would evaluate in nanoseconds, that would take too long. So basically, it's importance sampling, really. It's the same that Lattice QCD uses. Instead of sampling their entire parameters or their entire space, which is way too large, they just sample according to another distribution, which happens to be the distribution you want to have. And that works for Bayesian inference, but not for evaluating chi-squareds. Okay.
Yeah, Govert,
yes?
can I chime in? I don't know if I'd agree with that. You can do, it's much easier, for example, to find a minimum of a multi-dimensional distribution than to sample the entire distribution, which is what we have to do for Bayesian inference. It's not, you still have to sample a lot, but you can use, you can use MCMC to try to find the maximum of the distribution. Certainly. So I'm not sure I understand the difference between.
I mean, of course, once you have done the Bayesian inference, you can go back to a frequentist setting. But then, I mean, the computation with using the MCMC, that's just more intuitive in a Bayesian setting, I think.
I see.
And, I mean, you can find a minimum, of course, but then without an MCMC, I'd say the chances of getting stuck on a local minimum are larger.
Well, you can use the same. Well, okay, if you mean in terms of more intuitiveness than in terms of technology, I certainly agree. I think that the intuition we get from Bayesian is infinitely more than what we get from the chi-square. It's true. I agree.
Okay. So then I'll move on. So just a sample of the data that we used in our fit. So we have some integrated observables. So DND, I think it should be DND. Yeah, DND ADA. So particle yield. We have MePTs for pions, kaons, protons. We have VNs, and this PT fluctuations, and then this is for 2.76 TV, and then below is for 5.02. And then for each of these, you can also see, like, you have the data, which is the points with error bars, and then there's the the bands are sort of the posterior that comes out of the Bayesian analysis. So you can sort of see how well you're fitting. So we use these integrated observables, but also PT differential observables. So we have these pion spectra, again 2.76, 5.02, pion spectra, kaon spectra, proton spectra, and then we also use PT differential V2. It's weird, I have to point that way to make it go there.
I mean, it's a accelerometer. It's not. It only knows where you are when you push the button, and then relative.
Oh,
to there,
you have to keep pushing the
move it.
button.
You just hold it. And
Oh, okay.
Point it before you push the button, then it'll be centered better.
Okay.
you
It's
hold
just an
it.
accelerometer. It
Yeah.
doesn't know
Ah.
where it's really pointing. It's just relative to when you push the button.
Yeah, so we have the V2 for pions, kaons, protons again. And just to see why that's relevant, this already was discussed earlier, that in this first analysis where this paper is, where this plot is from, we found a much lower bulk viscosity than other groups. So you can see that here is the posterior for the bulk viscosity. And we found that that's mostly because of the inclusion of these PT differential observables. But I would like to stress that it is important to at least try to expand your set of what you fit to as wide a range of data as possible. Of course, I added this within reason yesterday after JF's talk, where I totally agree that if your model doesn't describe that observable, or you have reason to doubt it, you should probably not include it. But here also with my remark that I made yesterday, like you can sort of check how sensitive you are to, or well, you can check how well you're doing by varying, in this case, the highest PT bin. So you can see here the red is using integrated observables only. And then the other curves are where we change the topmost PT differential PT bin that we included. And then you would sort of, for example, expect that your hard contributions come in at higher PTs. So then if you see a lot of variation as a function of where your highest PT bin is, you would see, well, then you're probably measuring hard processes and not the soft stuff that you want to see. Yeah.
I mean, the functional dependence of the V2, the Vn of PT, is significantly affected by the particularization assumption. So you used PDP and you didn't explore the others. But since you point out that the fact that you get a much lower bulk viscosity than others comes from the inclusion of the PT dependent observers, I would be very worried that this reduction of the bulk viscosity is not robust against changes in the particularization.
Well, that's actually the reason we made this this plot, because our referee also asked the same question.
Just to put it another way, like I wouldn't make this so strong. Like it's not only useful to exclude a piece of data if it's unreasonable to compare that observable to your model because your model just fails. There's lots of other reasons, and one that you don't probe by doing analysis within your model is the theoretical uncertainty based on things that are not in your model. And in this example, it's uncertainties in this particularization, which you can't quantify in your analysis because you only had this one prescription. And so there's theoretical uncertainties that are there that are unquantified. And depending on what kinds of questions you're asked, this can be a big problem. Like the idea of this Bayesian analysis is to not only get a precise but accurate value for some parameter, but also an accurate estimation of its uncertainty. And so here you've reduced the uncertainty band seemingly by a lot, but potentially there's a large unquantified uncertainty.
It's precise, but perhaps not accurate.
But there is also a reason why I think it's relevant that we change the uppermost PT bin for the freeze-up prescription, because the changes in between the prescriptions are mostly in the high PT tails. So
that's not true either, really, but.
Why not?
Because, I mean, let's not, you can't make a generic statement. So for what we usually do for shear delta F, those differences in different models that people have done are usually high PT. But even that's not true for the bulk viscous corrections, which can have large corrections, even at low PT, because there's, well, for various reasons. So anyway, it's certainly relevant. It's good that you do that kind of study, but I disagree that you should only disregard data if like your model is just not, you know, unreasonable compared to the model. There's really good reasons other than that, and one of them is that you may get a misleading you know, error bar in your posterior because of unquantified.
Well, I mean,
theoretical
we
uncertainty.
can avoid that discussion by stating clearly that your results are conditional on the prior assumption that
Absolutely.
PDB is.
It depends on the question you're asking. As long as you're clear what you're doing, it's all fine.
But that you always, like, if you write a paper, you always put that in the introduction, right? That you, what you used. Yeah.
I totally agree with what Matt is saying, but again, I understand that including these differential observables is also what you did and was not in the previous Bayesian analysis, but it's important that for this, what we are doing, we're not going to use them anyway. So
it's just the
we shouldn't
introduction.
spend too much time on this because this is
Yeah, that's
completely
true.
irrelevant for anything we're going to do here.
I mean, it's somewhat relevant, like the discussion of what observables do you include and what observables do you not include.
Yes.
And it's kind of relevant for this exact reason. It's almost the same reason why we say for our purposes, we probably aren't going to use differential observables for that exact reason.
But yes, because they are not, okay. Yeah.
Because they will introduce a large theoretical uncertainty that we can't.
Yes, and the other reason is that they are
What time
not
is it?
sensitive
No, I
to what
think
we're
that-
probing.
I think that he, let's move on because he has results to share.
Yeah, so I've reached the summary of what I'm going to be talking about. So this is in my opinion, a very nice plot that Giuliano made after quark matter, showing sort of our history, sort of an initial state history, which shows our evolving understanding of the initial state, and it's sort of interesting that it looks like the initial state took sort of like a circle journey, what he calls it. So, for example, if you look at the nucleon size, which is this red dot here for illustration, you see it starts out very small, and then in later analyses it grows some more, and now here it's back to where it began. And another thing is this energy deposition goes like, I'll get back to what this exactly means, how this works. It went from TATB to the 2/3, where the power is what you should be looking at, to square root, and now back to 2/3. And you might ask, like, did nothing change? Did we just, as he said, go in a circle? Well, no, because sort of the reason why this happened is that the pre-hydrodynamic stage drastically increased in complexity. So, for example, the reason why this width is so small here and it's larger here is because in this paper, they introduced for the first time a free streaming pre-hydrodynamic stage, which makes a lot of initial radial flow. And to compensate, the Bayesian analysis makes the nucleons larger, so to decrease gradients, so that the mean PTs are correct. And likewise, so this one has no initial pre-hydrodynamic stage whatsoever. This one introduces the free streaming, and here we increase it in complexity yet again by interpolating between two different models. And that's exactly what the next three sections are about. So I'll be discussing this nucleon size, then this generalized Trento formula, this is energy deposition, and then also the strongly coupled pre-hydrodynamic stage where we interpolate between weak and strong coupling.
The difference between power 2/3 and power 1/2 comes from whether you initialize the energy density or the.
Oh, that's a very good point. I'll get back to that. Yes, and so what is also nice for the purposes of this workshop is that these three topics also nicely give the opportunity to go through Trento plus the pre-hydrodynamic stage in its entirety from the start of the computation to the finish. So you should be walking away with a good understanding of how Trento works. So to start with the nucleon size. So when you start Trento, you start with nucleons which have certain locations. So for example, in nucleus A, let's call this nucleon A. It comes from nucleus A. You have a nucleon A at this location, and then similarly for nucleus B. And for the purposes of this talk, I won't wonder where those positions come from. That's where the structure comes in. And then you compute these thickness, or yeah, these probability density, or these density functions, where this weight, or this not the weight, the width comes in, and then you make these nucleons wounded with a probability equal to this, where the sigma GG is tuned to reproduce the proton-proton cross-section. And then what you do after this is that each wounded nucleon, so if with this probability you declare nucleon A and nucleon B to be wounded, and then each nucleon builds its energy into its nucleus thickness function. So you basically sum over all the wounded nucleons, and then you have this exponential, which is basically the same as here. Or well, no, it's not the same as here. It's here. This is the location of the nucleon, so that's the same as this XA here. And then you also have this gamma, which creates some fluctuations. So as you see, it basically normalizes the it's a normalization of the Gaussian. And these gammas are drawn from a gamma distribution with mean 1 and standard deviation sigma fluct. So with sigma fluct, if you make that larger, then you get more fluctuations. You make it smaller, you get less fluctuations. And then one thing I didn't include, but what we did use in our paper is that the actual formulas are actually slightly modified because we don't model the nucleon as a single Gaussian. We actually have constituents. And yes.
So the W in the first equation there.
Same as in the second. That's the same W as in the second.
Yeah, but the physics is in principle that describes in principle different, because the first tells you the distribution of the strongly interacting matter that collides with each other, and the second tells you where the energy after the collision is deposited. And it's not clear that that has to be in the same place which originated the interaction. So the W serves two different purposes here, and I think making it equal is a natural first assumption, but it's something when you change it could affect significantly what we are interested in here.
Yes, I'll in fact get back to that because I think well, I mean, I'll get back to this.
So for the rule A is nucleon distribution, nucleon fluctuation. So what gamma controls additional fluctuation for energy transition?
It's the normalization. So you have this thickness function, and like every nucleus or every nucleon deposits a Gaussian,
Yes.
and then the size of the Gaussian is drawn from this gamma distribution.
Oh, okay.
You need that to have the correct fluctuations in the PP collisions, otherwise you don't get the correct mechanism.
Otherwise, there would be none.
Yeah.
The model would imply that every PP collision has exactly the same. It's more natural to include fluctuations.
Well, you also needed to get the PT fluctuations right in lead.
I have a question. Is it important to have like, say you take into account that nucleon as constituents? Is it important?
I would say yes, but then we've never really got any strong constraints from the Bayesian analysis. So apparently, in the data,
it's like order 1 importance for very small things. So sometimes you do like proton lead collisions, and so then the shape of the proton matters a lot. And so if you just assume it's spherical, you get a very different answer than if you allow the shape to fluctuate this way. So there it's like order 1. For heavy ion, for large systems, it's very subleading. Okay, right?
yeah, I mean, we've never
for the
we've gotten
calibration that you
weaker.
showed, it would probably not have been important, but if you did use your model for PP collisions. you would
Probably, yeah.
absolutely-
I mean, that's why I didn't expand on it, I just left it as a
You
comment.
derive stuff from what, like, what do you use to, like, pattern distribution or something?
Well, I mean,
There's all this very
I can give you a very good-
parameterizations.
if you just check out this reference, that explains it very well.
You have to go the number of constituents, which is just
Yeah, but
a
then,
way to parameterize how much the shape fluctuates, in my view.
In a sense, there's no PDF used here. It just, everything assumed is a Gaussian, okay, like, in this
Very,
simple
very
approach.
simplistic, just a way to extract.
But in the
information
IP
from data
plasma, they will.
by
Well,
parameterizing
some
it.
constituents replace that single Gaussian by a sum of Gaussians for each of the constituents.
Yeah.
So it leads to granularity at the subnucleonic level, but the more you have of these, the smoother the distribution becomes.
But I think that the typical, like, if I look at the hygiene, what they do is there's a soft component in the particle production, would be like this. But then if you want to model the high PT stuff, then they put in PDF as a separate component, which produce a few, you know, a few number of particles. And yeah, there's no, like, I don't think that, is IP plasma actually have a PDF embedded from in their implementation?
So,
Awesome.
How they make assumptions about the rapidity dependence, which can be mapped directly on the structure function.
They do have small x, right? But I don't know whether they probably also don't use PDF. They just use some color charge.
Well, it's derived from the KLN model, which has PDFs, right? Or from the
No,
CGC
but-
model. which-
Yeah, CTC,
Yeah,
nobody uses KLA anymore.
Yeah, not in the KLN approximation, but in the CGC. More specific.
anyway, let's maybe move on because the number of constituents isn't really that relevant to what I'll be discussing next. So one very simple observable you can make is basically, if you go to this previous slide, you can see that if you, say that this probability is not realized for any nucleon pair, so you get no collisions, then you also get no event, right? So you can very easily count, like, how many times do you actually get a collision, how many times do you not get a collision, and from that you can compute your cross section, which is, here what you see is the blue is the emulator for the cross section, and you can see that there's basically no emulator error because it's, as I said, it's very simple, it's very easy to compute. So you see here this lead cross section is a function of 4 different parameters in the model, where I'd like to focus on this width, and you can see there's quite a strong dependence on this width, and the Alice data point that was measured last year is here. So this seems to suggest that the width should be quite small. And just to illustrate, previous analyses, including ours, found like something around here. Yes.
That applies to the W in the first.
Yeah,
iteration,
that's the first one.
not in the second.
The next slide will have the answer to your question. Or well, that has the first part of the answer to your question. And this is really a very basic observable. You would expect a model to get this right. So in fact, we are going to enforce that you get it right by fitting to it in the Bayesian analysis.
Govert, can I ask, should we be careful about thinking this is a basic observable? Because this is an observable, as you said, that is dominated by extremely powerful events. It's
Yes,
probably a very...
Yeah, you're right. You have to be careful in how you, like, actually we had a lot of discussions with the people who made this measurement on how exactly the measurement is defined. So for example, I don't think I know the exact number, but I think it's that they measured the particle yields up to 80%, and then they fit the rest with a Glauber model. And we actually, I think Wilke did a lot of checks that this is that we are sort of doing roughly the same thing, or at least that we can trust that it is indeed comparable.
This, I mean, this is the nuclear cross-section as a function of Rudess that matters here, right? And I think this small value is what you would get from just looking at the nuclear cross-section.
No, this is the lead cross-section.
I know, but this affects the lead cross-section because the nucleon size is an additional extension on top of the Wood-Saxon radius.
Yes, it makes it larger.
And so that is something that gets measured directly in proton-proton collisions because that measures the size of the nucleon as it increases with energy.
But we
If
compensate.
you do that, then you do get these smaller values for W.
But we also compensate the proton-proton cross-section to, like, we fix that at
It's sort of independent because the total cross section, which I think is the measurement you're talking about for proton-proton, is fixed by,
yes, that's
you
fixed.
know, right, by hand. This W is just telling you like more detailed impact parameter dependence
Yeah,
of the cross section.
And what is also important is that you can see that there's really not a lot of dependence on the.
No, but sorry, I mean, the way you are doing this, if I'm not mistaken, is that you keep the Wood-Saxon radius R0 fixed.
Yes.
What I'm saying is what you really need to do if you want to keep the cross-section, the nuclear cross-section constant is if you increase W, you have to decrease R0.
That does make sense. Yeah, that's a good point. But I cannot give an answer now. What would happen if
Depending on what R0 is, right?
The opposite, your nucleus is going to make the nucleus bigger.
And that was pointed out by Yasushi Nara and Tetsuhiro Fumi ages ago, and somehow that historical insight has gotten lost.
Right. So if you add one more plot for different W, what is the refitted R0? And then
yeah,
we will
that's
take a look at, I mean, that will tell you what's the how much impact it is.
yeah, but
Maybe if I can comment, so you know, first to Jean-François and then to Uli, because my we call this a basic observable because it only depends on 4 parameters theoretically. So theoretically, it's very basic observable. Experimentally, you're kind of right that it's difficult to measure, but they actually managed to get it very accurately, like within 2.5%, which is dominated by the luminosity uncertainty. So, okay, I mean, we have to trust the experimentalists, but we talked a lot with them, and we do trust them. And yeah, so theoretically, if there is a collision or not, it's very clearly defined, and it only depends
is that
basically on the
true?
width, actually. The definition of the cross section is really if there is a single interaction that causes a single particle, and then you can wonder if it's like within which rapidity window, but it's not even very dependent on that because Ali's coverage is like very large. So
Well, I can ask after you've made your second point if you want, or I can ask now. I mean,
Yeah,
what I'm okay, make your second point. Sorry, go ahead.
okay, to Uli, we thought, of course, very carefully about that. If the R0 needs to be changed because the width changes, but in our point of view, this large width that was previously found was not necessarily that the nucleons are really that large. It was more that, at least at rest. So I mean, R0, of course, measures kind of how big is lead nucleus at rest. And one of the ideas of this nucleon width, why it would be so large, is that if you boost it to very high velocities and you collide it, that this long cloud would really be very wide. And so it's not necessarily, so what we take in our model is the point density of the nucleons, this R0. So there's, of course, the Wood-Saxon has charge density and a point density, and the point density is where the mid-center of the nucleons are. And charge density is slightly bigger because there is this width, and that's taken
If you
into
keep
account.
R0 fixed, then the total nucleus cross-section increases in direct proportion with W.
No, it's square root. It's square root R squared plus W squared. It's actually a very small effect also.
Let me propose something. People should think about this question, and we will discuss in the afternoon because otherwise we will not be able to converge.
yes.
So let's continue. We have 30 minutes left.
Nowhere near halfway. Yeah, so there's another reason to think that the width should be smaller, and here you're really talking about the second width So here, this is a paper by Giuliano, Björn, and Chun, where they compare basically the Alice and Atlas data to model calculations with assuming different W's. And so, well, the trajectory result is not plotted, but it's very similar to the Jetscape result, which is, well, sort of like this. So you can see that's, oh wait, this is the initial state predictor. So it's similar to these curves. So you see that it basically goes negative way too soon. Whereas if you decrease this width to around 0.4, then it's much more compatible with this rho observable, which previously was mentioned. This is the correlation, the Pearson correlation coefficient between the V2 and the mean VT.
But you don't use this variable for calibration.
Well, not yet. If I get to the last slide,
Okay.
I will comment on that. For now, I'll just say it's a very, it's a statistically challenging observable. It's very expensive. So at least when we did this, it wasn't really possible to directly fit to this, but cross-section is a lot cheaper, so that was possible.
So in this ways corresponding to proton charge radius rays.
Well,
Less radius.
it's the same W that you saw on the previous slides. I mean, I didn't make it green here because this is a PNG, but so it's the same W.
Oh, I know. I mean, in this way, it's corresponding to the proton or neutron less radius rays.
It's just the model parameter company. So what happens if you actually do this? You include, well, we included both the lead-lead and the P-lead cross-section. The lead-lead was measured by Alice and the P-lead by CMS. And so we also include these 3 different fitting scenarios. So this weighted, unweighted. I probably will skip this. So well, there's 2 different fitting scenarios, and then also integrated observables only. If you don't trust the PT differential ones, there's also integrated. And then you see that if you don't fit to the cross section, you really get this very large, these very large values for W. And if you do fit to the cross section, it's a lot smaller, around like 0.6. And I would say this is also natural because, like as Chun said, that you would expect this W to sort of be roughly equal to the charge radius of the proton, which is known. So I would say this makes sense that it should be smaller. So what are the consequences of this? If you make the nucleon smaller, you increase radial flow, and that would increase your mean PD. So it needs to compensate somehow. How the Bayesian analysis compensates is by making the bulk viscosity larger. So previously you saw like we had this very small bulk viscosity, and now it grew again to be quite a bit larger due to this. And another thing that is sort of strange is that it also seems to invert the slope of the eta over S, which is quite strange, but this is very similar to what the Bayesian analysis using IP Glasner presented at Quark Matter. And going back to the to this rho observable, now you see that if you so this one is without the cross section, the red one, and you see it's very well. This is very bad fit with the experimentally measured observable, but then the blue band is the sort of our posterior, including the full uncertainty from the posterior. So you see that the agreement is much improved. So also for this V3, so previously it was negative, now it's positive and compatible with the data. But there are still some puzzles, because if I make the same slide for Atlas, then the agreement is quite a bit worse. Still okay, it's still clearly better than before, but now we're overshooting it. So it's sort of unknown what the reasons are. Kinematic cuts are different. So maybe if you do 3+1D simulations instead of 2+1D, maybe you resolve this. Also here, I'd like to stress it's important that we match the precise experimental procedure. seems to be quite sensitive to various choices you make.
I made a proposal that Emil or somebody should discuss the difference between Atlas and Alice measurement for these observables, like probably next week, if possible. Because the difference is quite big, right? I mean, if you go back one more slide, that one more, right? You see the
One more?
One more, yeah. Yeah, this one. You see the open circle, the circle is Alice measurement, the diamond is Atlas, right? And for both observers, there's a very big difference. Especially for V2 PT, if you think that there's a huge difference. So I think, okay, your uncertainty is big, so you can hide a little bit, but there's really some issue there.
I mean, the difference actually is not that large, right? It's just a few percent, and actually these PT cuts, they're very important, like 0.5 or 0.2, and also Alice measures multiplicity, Atlas measures centrality, Atlas measures centrality versus energy, and we find that also makes, very big differences.
Yeah,
No,
we check those. We check those.
This is no, I don't think it makes a difference.
Yeah, we in the
PT cut,
Xenon.
maybe the PT cuts,
No, we in the Xenon we can check the PT cut in the Xenon system. And there are some change, but much smaller than this difference. In LED, we cannot check, right? We have to start from 0.5 GV, but for Xenon, we can check the PD dependence. It takes somebody to.
But I need to check it too.
Yeah, we did where we varied both the lower PT cut and the upper PT cut. And it does
What makes it
quite a big difference, especially, I believe it, especially the lower cushion cutoff.
But look, on the other hand, you stop at 70% centrality, but if you stop at 80%, you see we really good negative, and at least probably we never good negative. Okay,
It's a minor point for this. For this, I put it in because I thought I'd have too much time. I gave the same. I gave roughly the same talk at Duke, and it was 60 minutes. So, so where is my mouse? I'm gonna go forward. So where we left in the description of Trento is that you had this these two thickness functions. Of course, you should initialize your hydro with only one stress tensor. So the question is, how do you do this? And what Trento does is it combines them using this formula. So you raise both of them to the power p, take the average, and then you raise to 1 over p again, and then well, you can see that for 1, obviously you just get the average. Here you get the what's called, I think, the harmonic mean. And then for 0, it's a bit of a weird limit, but you get this square root TATB. And what you can already see here is that there's no setting that gives you binary scaling, or in fact any other power other than the square root. And so what I really always like about Bayesian analysis is that you can use this to sort of test microscopic models, not directly, of course, because it doesn't correspond one-to-one with these microscopic models. But for example, this is the posterior from the Duke group, from Jerna Bernard's thesis, where you see the posterior overlaid with a couple of microscopic models, and you can really see that this wounded nucleon and KLN are very much outside of the posterior, so you can sort of rule them out, at least in terms of how they scale. But both EKRT and IPGlasma are within the posterior, so you have a little bit more confidence that probably the assumptions going into into these models are probably the right ones. And this is also this sort of also introduces the general workflow for both this section and this section. But if you want to test a theory or ask a question, what you can do is you introduce some parameter which parameterizes the question. In this case, how does nature scale? And then you confront this generalized model with data using Bayesian analysis, and you read off the posterior and draw your conclusions. So what we did is we were at first interested in binary scaling, but it turns out you can do a little bit more with it even. So what we basically just did is where you see this Q, there used to be a 1, we just replace it with a Q. And then it's quite obvious that you can get this binary scaling, which was just this, well, turning the square root into not a square root. That if you just set this p, you keep this p to 0, and set q to 2, then you have binary scaling. And what is also going to Uli's point, that if you assume that the equation of state is conformal, which, well, to some approximation it is, then if you set q to 4/3, you can also look at this difference between the between viewing the result of this, so this combined thickness function, viewing that as an energy density or an entropy density. And that's also another change that was made historically in this, going from this 2016 paper to the 2018 paper from the Duke group, that they started interpreting it as an energy density, whereas previously they interpreted it as an entropy density. So now, confronting this with the data, what you find is like this blue posterior. So it's, you see, it's not 1, it's sort of 4/3. So that goes very well with the picture that maybe the first analysis was right, that you should probably interpret this as an entropy density. And what you also see is that it's also sensitive to this width. So if you set the width to be very large, then the Q posterior is centered around 1. So if you just force it to be large, and as you decrease W, if you just fix it, then the Q rises. So these are clearly correlated.
First show the solid blue. What does that assume for them?
It lets it float freely. It lets it choose by itself what it wants. But it does fit to the cross section. So it's assuming that you fit to the cross section. So then another interesting question you can ask, like I said, you can sort of test theory. So how does this compare to IPGlasma? It turns out from this reference that IPGlasma scales like this. So, well, unfortunately, we don't really capture the IPGlasma scaling. But if you assume that TA and TB are roughly the same, then that reduces to this. And that corresponds to Q equal to 1.5. And if you then look at the posterior again, you see that this is on the high end, but still compatible with the experimental data. So we sort of rule in IPGlasma, at least for now. And what is, of course, an interesting thing you could do in the future is to explicitly put this in and see if, for example, it's preferred over the previous Trento formula that we had, or maybe it's not preferred. I'd have to try it out. So going to the last section, we also modified this in this pre-hydrodynamic stage. So previously this was done by free streaming, and I'll get to what that is in the next, how that works in detail on the next slide. But first I'd like to give like a sort of our first attempt at this. So there's this paper by Wilke, Paul, and Scott, where they use ADS-CFT to compute what happens in the initial stage of anti-ion collision. So ADS-CFT assumes infinite coupling, among other things. And what they found is that the shear and bulk pressure quickly relax to their hydro values. And what are those? Those are basically that if you take these, just the first order terms in this 14-moment approximation, which I'll flash later, and you just set this equal, and then by analogy, I mean, this is a conformal calculation, but by analogy, you can say that the bulk should do the same.
These are the Navier-Stokes values.
Yeah.
Hydro,
Yes,
hydro
exactly.
doesn't have to be on Navier-Stokes to call them hydro values.
Yeah, sure. That's but so in free streaming, what you can see here, if you compare the red with the blue, you can see that, for example, for the bulk pressure, free streaming doesn't just have a very different order of magnitude, but also the different sign. You can in fact see this if you initialize your hydro with free streaming and then let the hydro run. You can see that the bulk pressure sort of immediately changes sign when you start hydro. And what we tried in this initial paper is to use a sort of free streaming velocity, so not free streaming with the speed of light, but with some other velocity, to sort of mimic this effect. So you can see that if you change this free streaming velocity, you sort of change the behavior of the initial bulk pressure. Of course, this isn't really right. We don't really believe that it free streams with 0.9 the speed of light. So in this work, we try to do it right. Let me first explain how free streaming works. So what you basically do, you get your, so you have your Trento, which creates your matter at a proper time tau 0 plus. And that's basically given by this generalized thickness function. And then you can sort of do this free streaming. You can do analytically, you just compute this integral around sort of in the past light cone of the point at time tau hydro where you want to initialize your plasma. And then yeah, and then you can also see you get this 1 over tau hydro due to the longitudinal expansion. You can see, yeah. So this is basically what free streaming does. Now, how to generalize it is with this. So we introduce this R hydro parameter, and what it basically does is you have this next to this free streaming computed values. We also simply put in the Navier-Stokes values, and then we use this R hydro parameter to interpolate between the two choices. So then you immediately run into a problem because this completely fails. And I put this in because it's a nice illustration, I think, of how Bayesian analysis can be hard. So imagine that you have a shear viscosity which very quickly rises as a function of temperature. Now imagine that you also are initializing your hydro at a very early start time. So temperatures are very high. Also, your Trento norm is very high. So the overall normalization of all of these Gaussians is very large. Then it turns out under those assumptions that you initialize your, like by doing this, you initialize your shear stress so far from equilibrium that you produce a lot of entropy through viscous effects, and you get a final state with like 50,000 particles. Now what happens? You, in the first try for this, we used EuroQMD. You feed your 50,000 particles into EuroQMD, crashes, because it wasn't designed to handle that many. Then, so whatever result you get out is going to have a lot of missing events. And so the error bars are going to be enormous. And then the Bayesian analysis will think, okay, error bars are large, so the discrepancy between theory and experiment is fine. So your Bayesian analysis will start preferring those values, whereas they're really ridiculous because they have way too many particles. So how do you fix this? Turns out that if you go to second order, so you use this full 14-moment approximation, you get rid of this problem. So what we do is you basically say that you set the left-hand sides of this to 0, and then you simply solve for pi mu nu and for capital pi, which you can do because it's almost linear. This phi-7 term is the only one that's not linear, and you can just use Newton-Raphson to get that from an ansatz using only the linear terms. It turns out that for most design points, this doesn't really make a difference, but it makes the problematic ones less problematic, and then the Bayesian analysis can properly exclude them because.
Let me understand what you're doing. So if what you showed before, which you said fails, is setting the left side to 0 and ignoring all terms except the first two.
Exactly.
So it means what you are telling us is that what's the cure is to the other second order dissipative effects.
Yeah.
You have to include those.
So you're basically assuming that it gets time to reach whatever, well, equilibrium is reached by these equations, which you're basically doing by saying like, whatever happens here happens at a longer time scale, at a shorter time scale than this tau.
But now you become sensitive to the choice of the red transport.
That's true, but So for the reasonable parameter choices, so not very large shear slope combined with very short initialization time plus a very large norm. For parameter choices that are not that, it doesn't really matter that much.
My understanding is that there is more difference between hydro and free streaming than what you get, but when you vary the hydro, it doesn't change this initial stage too much. Is that correct? Because you have a bigger effect from interpolating between free streaming and hydrodynamics than by varying the transport coefficient.
Yes. Well, I mean, my main point is here that like that one of the difficulties of Bayesian analysis is that you have to make sure that your model works everywhere, including for parameter combinations that are clearly wrong.
So what you're saying is far off equilibrium, the stationary point of Stewart or whatever, is not the Navier-Stokes value, but the new value that you're calculating in this way.
Yeah, and if you don't include that, then whatever you're doing in your Bayesian analysis will go haywire.
So there are 15 minutes?
Yes. I think I'll actually get through it. So what do you get in your posterior? So what you sort of immediately see is, so remember this 0 basically corresponds to free streaming. 1 corresponds to using the ADCFT inspired result. You see there's a very strong preference for the ADCFT value. And what you can also see is that if you fix this initialization time at different values, you can see the preference becomes stronger if you increase this hydro start time, which also makes sense because basically the free streaming drives it away further from the equilibrium where it wants to be. So if you let that go on for longer, then it, well.
Is this constraint mostly coming from the MPT?
So
if you don't think we know. MPT, like because the free streaming mostly enhanced MPT, right? A lot.
Yeah, it probably plays a big factor. I mean, you could try this by redoing the Bayesian analysis, deleting the mean PT data.
Yes.
But then that's a lot of work to figure that out, I guess.
Is this already published or is this part of the?
This is the 2302.xxxxx.
Very nice.
I just included this last bullet point yesterday because I thought of Uli's comment earlier, that you can sort of see this as this model averaging where you compare 2 different models. But I would also like to say that this is in some sense, a cheaper way to do this, because what you could in principle also have done, like, I don't even know how to interpret these values in the middle. They interpolate between 2 different models. But so in principle, you're really only interested in the endpoints, right? So you could in principle have made 2 different emulators, one where this is fixed to 0, another where it's fixed to 1. But that would basically require you to run your design points twice. So you basically double your computational cost.
Not if you use transfer.
What?
Not if you use transfer.
Okay, sure. But this is also a cheap way to deal with that, because if you so it's sort of a heuristic in Bayesian analysis that the number of required design points, if you want a specific kind of uncertainty, then the number of design points that you require is roughly proportional to the number of parameters. So if you already have 20 parameters and you're just adding 1 extra, it's like 5% extra cost. So that's fairly cheap to do. So the last thing that I wanted to talk about is something we introduced in this paper from last June. And in fact, since these 2 papers come from the same analysis, actually it's also used in this one. And that we introduced weights. And in principle, this is a little bit strange because in principle, the experiment tells us with their uncertainties what our weights should be. They should just correspond to the uncertainties. But what you can sort of do with these weights is that if there's a region, for example, where you trust your model less, like for example, we do it higher higher PT values or very peripheral bins, you can sort of artificially increase your error bars there to indicate that you have less trust in your model in those regions. And another related point why you might want to introduce weights is that we don't have the full experimental covariance matrix. So just to illustrate this, here I have 4 different plots, each with the same variance in X, same variance in Y, and the black dot is at the same location, but I'm varying the correlation. And you can see that it goes from being within 1 sigma to being well outside 2 sigma.
But
So-
the experimental error bar is so small, you probably shouldn't care.
Well, that's,
the most
yeah, I don't have a plot of this, but like there are many observables where the experimental error bar is already the leading source of uncertainty in our Bayesian analysis. So this
For which example?
well, mostly the simple ones. So like the particle yields.
Those are systematics dominated, also not statistical, so you need to understand.
Yeah, so you need to, what we really would like to have, I know that this is experimentally very hard to do and like a lot of work, like what we really like to have is like the systematics covariance matrix.
Certainly for flow observable, the error bar shouldn't really enter. Like
Yeah, for the flow observables, we're still dominated by our own theory errors.
We're still fairly correlated though, right?
No, the error bar is so small, you know, it doesn't matter.
But at some point, we're going to improve this enough that this is going to become
I think that the yield is indeed, that's typically normalization uncertainty is quite large.
Anyway, so so if you have observable classes which are correlated, so for example, say you have a whole bunch of PT bins for the same observable, and if you get the correlation wrong, so like what we do right now is we guess the correlations, not just we. I know that the Duke group also made an educated guess, and I think Jetscape is doing the same. But if we make the wrong guess, then an entire class could be given more or less weight than it really should have. So what we basically did is say, I mean, we're not arguing that this is the solution. It's just that we thought it's better than doing nothing, or at least we're going to explore the problem. It's basically, you saw this formula in Jean-François' talk yesterday, where you have this difference between theory and experiment, and then you sandwich this inverse covariance matrix with those differences, and you get this conditional probability. And basically what we did is around this covariance matrix, we just include this omega twice, where omega is a diagonal matrix containing the weight for each observable. So what did we choose for this? So we did a couple of things which are basically just our choices. You could choose something different. We just wanted to try out what it would do. So we say, like, for every particle identified observable, we give a factor 1/2. Then if an observable is PT differential, then above 1 GeV, we start giving this penalty factor. And then if a centrality class is beyond 50%, we give this penalty factor. And what you see basically is that if for example, you compare this column with this column, what you see here is the average discrepancies. And you can see here that it's basically 1 is above 1, and the others are all below 1. And then the sigma, the cross section is above 1 again. But this is strange. They should sort of be 1 on average, or, well, I mean, really the square of this should be 1 on average, but we didn't plot that. This is sort of a strange distribution that you do a whole lot of observables too well, basically, and then you do a couple of them very poorly. If you include these weights, you see that it's sort of more reasonably distributed. So what we think is happening is exactly that if you, for example, if you have these correlations and you're doing the correlations wrong, then say, for example, taking an extreme case, if you have 100 correlated observables and you give them slightly too much weight by assuming they're less correlated than they really are, and you compare with one observable, say your cross-section, then the cross-section starts being underweighted and the 100 correlated ones start getting too much weight. And then you would see, for example, the Bayesian analysis trying to make, say, the correlated observables have like on average 1.1 sigma deviation. It tries to make that into a 1.0 at the price of making the cross-section into from 1 into 4 or something sigma. So then,
what's the W bar in the last column?
oh, it's the average weight over this class. So we grouped things together. We grouped observables together, and then if you follow this prescription and you take all of the observables in that particular group, then you arrive at this average weight.
If the weight is small, means they are less important.
Yes.
So the flow doesn't play. I mean, the flow is very important, right? Why you reduce the role of the flow observables? I mean, the spectra play a biggest role.
Because they're both PT differential and identified.
Oh, where's the integrated flow? Oh, I see.
There's
There.
a third.
Okay, so there you have a weight of 1. Okay, I see.
Okay, so you're now doing exactly that, you say, okay, this PT differential, so it should be not really taken very seriously in the calibration.
Yeah. Well, I mean, you're doing something between that shouldn't be taken seriously at all, and we should take them very seriously.
Yeah.
So then you can see what difference it makes. Like, so here we have this, you saw these colors before, you have this weighted curve and the unweighted curve, and then you also have the integrated observables. So say that you, for example, this is basically choosing all of the PT differential observables get weight 0. Just completely ignore them.
Mm-hmm.
And then sort of, for example, something like this, you clearly see that if you include these weights, you're sort of making it less, you're making your, for example, your freeze-out temperature in this case, less precisely determined, which makes sense because you're throwing away a little bit of the information on particle identified observables.
So, yeah, I mean, this temperature is fixed by the chemical composition, and now we are giving less weight to the yields.
Yeah, because they're particle identified. So, well, I guess I'll leave it at this. So we included the cross section for the first time. We looked at the scaling in Trento, where we saw that like this binary scaling is very strongly disfavored. So Q is 2 is very much outside of posterior. We also found that probably, or well, I mean, in our model, you can sort of see this reduced thickness as an entropy density now instead of an energy density. And the scaling behavior of Trento is compatible with IP plasma. And we have this interpolation between a hydrodynamic stage which has, or pre-hydrodynamic stage which has 0 coupling, which perhaps isn't very realistic, and one that's infinite coupling. And this is actually also something you could try and improve in the future, because, for example, you could say you put a weakly coupled kinetic theory or something and compare that with ABCFT and then see if you still see a difference, because probably 0 coupling is a bit extreme. And also that we introduce this weighting where, well, I mean, you can see how much it changes. And so for the future, we very much improved the statistics. So we can actually now, so this is also with around 20 hours of computation on a laptop, you can now get this row observable. And this is roughly also what you'd be able to do on a cluster, so per design point. So it's probably good enough that you can include it. And in fact, we are including it in our current run. Also, things we want to do is this to do a Bayesian analysis with 3+1D simulations. And also this nuclear structure with oxygen and neon, which you already saw a bit in Giuliano's talk. And also maybe something that is actually quite simple to implement is to just put this the formula for this Trento scaling directly into the Trento formula, and then maybe interpolate with yet another parameter between the Trento formula and epiplasma scaling, and see if you can if you can find a preference for one or the other.
So you said just need 20 hours in a single laptop. Is this?
It's a gaming laptop, so it's
No,
a bit
I'm
cheap.
saying,
But
is this so this is a full hydro simulation?
yeah, full hydro plus the afterburner.
And this is oxygen or?
No,
this
it's
is
lead.
Oh. How many events for this?
It's 20,000 events with oversamples. So if you count the number of the oversamples aren't really
Sure.
distributed equally among the centrality, but
So
the total number of oversamples is something like 500,000 or so.
So 20,000 hydro events for all centrality interface.
Yeah.
Okay.
So that was it.
Yeah,
Perfect
so,
timing.
okay, we start late, that's why we also hit that a little bit late. So there is a, okay, there's a comment.
Oh,
no.
yeah, there's a hand. Do you have?
Okay. No, it's a
Oh.
collapse.
Oh, it's clap. Sorry, never mind. It's
Okay,
applause.
so, any burning questions? We had a lot of discussion already. So let's break for 30 minutes.
Hi, I have a question. Hello?
Hi.
Yes.
Yes. Hello.
Yeah.
I have a question regarding this generalization of Trento parameters. So you generalize it. Yeah, if you go back to the slide. Yeah.
Here?
So you introduce this parameter Q. So which was assumed to be 1 before, right?
Yes.
Yeah, so now you are saying that it is favored to use 4/3 instead of 1.
Exactly.
If we fix the width to 0.4 Fermi, let's say. So is there any comparisons like how this data is now fitted better with this Q parameter to be taken like 4/3 instead of 1? Like,
Yeah, that's always hard to say in a Bayesian analysis. Like data points jump around and like. Yeah, I mean, you could definitely, I think, answer your question, but we haven't done that yet.
yeah, so my question is, this introducing this Q as 4/3, does it improve our Trento model than the previous one?
Well, I mean, what like,
Over Q equals to 1.
in what
That
sense do you ask the question? Like, does it improve the description of observables? That, well,
No,
it's very hard
if
to see
we-
differences there, but like,
No, if we compute this row observables, and if we make a comparison with Q equals to 1 and Q equals to 4/3, if we run a full hydro simulations and compare this row observable with the data, let's say Atlas data,
oh,
would it be closer to the data with this Q equals to 4/3? Like, do you have any?
well, I mean, this is with Q equals to 4/3, but we haven't run it with Q fixed to 1.
Okay.
So I don't know if it would be worse.
Yeah, because I did with Q equals to 1, just only Trento and music. So at higher centralities, it was not really closer to the data, Atlas data. So that's why I'm asking that if there is some improvement with Q equals to 4/3.
With what kind of weight? I keep saying.
Oh no,
with what width? Because the width is really important.
with I think I choose 0.3, not 0.4. I did 0.3 and 0.5 and also 0.8.
So, Rupan, do you think you can share this information in the afternoon discussion? So if you think,
Okay.
Pretty late.
okay.
He's in France.
Oh, it's in French, okay.
So before you showed
But
this,
you can
you showed this nice plot from Jonah Bernhard's thesis about the Bayesian constraint on P. That's assuming Q equals 1.
Yes.
Now, when you change Q from 1 to 4/3 or 2, what does that?
Oh, how the P moves. I have that somewhere. Where is it? P.
So it does.
Still compatible with 0.
It's no longer nicely centered at 0, the distribution.
Yes. Well, I mean, it's also can jump around a bit from analysis to analysis, but it's,
And when P is not equal to 0, then the scaling is not square root of, it's not TA times TP to the 4 zeros, but something else.
I mean, we have a correlation plot, so P and Q are mildly correlated. So yeah, if you change one, you change the other as well.